So chapter 15, chemical equilibrium, part 5, last part of the first chapter on equilibrium. So you have listened to me talk about the kind of background conceptual stuff with equilibrium, and then you've gotten to listen to me do a whole bunch of calculations solving for things at equilibrium. Okay, so those are going to be important to moving forward, but for this last part, we're shifting gears and we're looking at something new. Okay, so we've talked about capital letter K, the equilibrium constant, a lot. And in all of our calculations, capital letter K, equilibrium constant, we can only put in numbers that we know for sure are equilibrium numbers, either equilibrium molarities or equilibrium pressures, into the equilibrium constant expression. That's the rule. You can't put initial numbers, right? You can't put, I don't know when numbers. Only equilibrium numbers can go into the equilibrium constant. So that kind of poses a problem when we're not sure if something's at equilibrium or not, because we're not able to put numbers that we're unsure about into the equilibrium constant expression. And so we needed something that we could use to help us figure out whether or not a reaction was at equilibrium or not. If you know the equilibrium constant, what it's going to be when it's at equilibrium, and you're doing a reaction, like, I want to know, is this at equilibrium? Well, I don't know. I can't tell by looking at it. It's not like it does an equilibrium dance when it reaches equilibrium or something. So one way to tell if something's at equilibrium is take the molarities of the chemicals the way they are now, put them and solve for basically the equilibrium constant. But we can't solve for the equilibrium constant if it's not at equilibrium. So the reaction quotient, capital letter Q, is what helps us out with this. I like the reaction quotient because it's a capital letter Q, and I think the letter Q needs more use. I've told my husband before that it's not the only reason that I married him, but the fact that his first name starts with a Q because his name is Quentin, makes me real happy. So anyway, the reaction quotient, it is what is considered I call it the right now constant. So capital K is the equilibrium constant. Capital letter Q, the reaction quotient, is the right now constant. It works exactly the same way as the equilibrium constant, with one exception. We're not held to that. It must be at equilibrium. So you can take the numbers in your reaction right now, even if you don't know if it's at equilibrium or not, put them in the reaction quotient to see what is the reaction quotient right now, and compare that to the equilibrium constant. So the reaction quotient, Q, there are QC values, there are QP values, and they still work with products over reactants. Their ratios are the same. That's an interesting way to spell reactants. The only difference between them is with capital letter K, in those products and reactants spots, you can only put equilibrium numbers. With capital letter Q, you can put the molarities or the pressures for any time into the reaction quotient to solve for them. And the purpose of this is to figure out if Q is the right now constant. Is the reaction right now at equilibrium? Well, let's solve for Q, and let's compare it to K. K is the constant that it should be when it's at equilibrium. Q is the constant that it has right now. Well, if the K number and the Q number are the same number, then doesn't that tell me that right now I'm at equilibrium? And if the Q number is different than the K number, then the right now number is different than the equilibrium number, so right now I'm not at equilibrium. So we're going to be able to answer the question, yes or no, is this reaction at equilibrium right now, using the reaction quotient. If the answer to that is no, it's not at equilibrium, we're also going to talk about how we can decide what the reaction needs to do to get to equilibrium. Okay, so in Q, you can put initial numbers. In Q, you can put after 15 minutes numbers. It doesn't have to be at equilibrium for Q. Okay, so like I mentioned, if the Q value, the right now constant, is the same number as the equilibrium value, the equilibrium constant, that tells you that you're at equilibrium. Okay, if the Q value is greater than the K value, so just a reminder, for both Q and K, this pen, they're equal to products over reactants. Okay, so I'm going to give us some scenarios. Let's say Q was 200 and the K value is 1.9. Okay, so right now the constant is 200. At equilibrium, the constant is going to be 1.9. So I can say with absolute certainty, right now this reaction is not at equilibrium because these numbers are different. Well, right now the constant is too big, right? It's 200 and we need to make it smaller. We need to make it go down to 1.9. So if we look at this ratio, if I want to make my answer smaller, which thing should I increase, the products or the reactants? So I want to make the number smaller. So should I make the numerator bigger or the denominator bigger? Well, if I want to make my answer smaller, I should make the denominator bigger. I should divide by a bigger number to get my answer to be smaller. So if this is true, if Q is greater than K, what that means is I need more reactants. And when we write out a balanced chemical equation, isn't it reactants here, products here? So if we need more reactants, another way that this is said is that it shifts to the left, because aren't the reactants on the left-hand side? I'm okay with either answer. If in your question you found out that Q was 200 and K was 1.9, I would ask, is this reaction at equilibrium right now? And we would say no, because Q and K are different numbers. And then I would say, what needs to happen for the reaction to get to equilibrium? And your answer could be either it needs to make more reactants or it needs to shift left. Both of those are correct. Okay. So we've talked about two scenarios. When the Q number is exactly the same as the K number, it means that it's equilibrium. When the Q value is bigger than the K number, it's not at equilibrium and we need to make more reactants. So scenario 3, when Q value is smaller than equilibrium. So again, both of them are equal to products over reactants. And I'm going to pretend that Q was 2.25 and K is supposed to be 12. Okay. So the right now constant, the Q, is 0.25. At equilibrium, the constant's going to be 12. So I can tell you that right now I'm not at equilibrium. Right now, my constant's too small and I need to make it bigger. So looking at this ratio, if I want to make this number bigger, looking at that ratio, I should increase the products. I should make more products. And when we have a balanced chemical equation, the reactants are there and the products are here. Aren't the products on the right-hand side? So another term for this is the reaction needs to shift right. It needs to make more things that are on the right-hand side. So if the Q value is smaller than the K value, no, it's not at equilibrium, and it needs to make more products or shift right. For me, I don't memorize if Q's smaller, shift right. If Q's bigger, shift left. It wasn't worth that. I just think of this ratio and which one needs to get bigger in order to make the Q become the K. Okay, so let's try one of these. Okay. Oh, I forgot. I just wrote it in words. All right, so here's an example. Here's my reaction, and I'm telling you the equilibrium constant, the Kc value, is 50.5. Okay, so one thing that I had said in previous videos is the first thing that you can do is write the equilibrium constant expression. Okay, I'm not changing that. We can still do that. Now, what we can do now is when we need to, we can also write the reaction quotient expression, which, by the way, looks exactly the same. The only difference is the numbers that I can put into Q do not have to be at equilibrium. The numbers that I put into K absolutely 100% have to be at equilibrium. Okay, so here's our question. Predict in which direction the reaction will proceed to reach equilibrium at 448 degrees Celsius if we start with 2.0 times 10⁻² moles of HI, and that much of hydrogen and that much of iodine in a 2.00 liter container. So the question is asking, this is what I'm starting with, these amounts of chemicals. What does the reaction need to do to get to equilibrium? So anytime we're trying to tell if a reaction's at equilibrium or tell what needs to happen to get it to equilibrium, that's a reaction quotient problem. These numbers are initial values, right? We're starting with those. So what we need to do is solve for Q and then compare that to K. Now, when we're looking at equilibrium constants and ice tables, the only units we're allowed to have are molarity and atmospheres. That's true for Q as well. So these moles need to be converted to molarity before I can do anything. So that's what I'm going to do first. I just took my moles and divided them by the volume, which is 2.00 liters. What I'm going to do now is take these three numbers and plop them into my QC expression. Okay, I wrote that on the previous slide, but I just took that equation and then plopped in our numbers, and what I got was 1.3. So Q is 1.3. Right now, it's 1.3. At equilibrium, it'll be 50.5. So I can say with absolute certainty that we are not at equilibrium. Okay, we're not. We're just not at equilibrium because those two numbers are different. So what we need to decide now is what needs to happen to get it to become equilibrium. So right now, Q is 1.3. And that Q needs to get to 50.5 in order for it to be equilibrium. So this number needs to get bigger. So which do I need more of, the HI or the hydrogen and the iodine? Well, if I want my number to get larger, don't I need more of this? So I need more HI, which HI is a product. And the other term for that is I need to shift right. Typically with these reaction quotient questions, there's going to be two parts. Is the reaction at equilibrium, which is a yes or no question. In order to answer that, you have to solve for Q and compare it to K. And then the next question will be, if the answer is no, if it's not at equilibrium, what needs to happen to get it to equilibrium? And that's when the answer is either going to be, shift it right, shift it left, make more products, make more reactants. Okay. So that's how you're going to identify these reaction quotient problems. So the last thing we have in chapter 15 is conceptual, no math. Okay. But it's really important, and we're going to use it in chapter 15, 16, 17. You're going to see it in organic chemistry. It's not going away. It's called the Châtelier principle. That's how you say that. So the official definition of the Châtelier principle is there. If a system at equilibrium is disturbed by temperature change, pressure change, concentration of one of the components changed, the system will shift its equilibrium position to counteract the effect of the disturbance. Okay, so in regular words, when a reaction gets to equilibrium, it stays there. It's going to stay there until someone screws with it. And by screwing with it, you change the temperature. You poured more chemicals in. You poured some chemicals out. You, if it's a gas, change the pressure. Okay, so you screwed with it. The Châtelier principle says, once the reaction that used to be at equilibrium, and then you screwed with it, it's going to respond by trying to undo whatever you did. If you poured in more chemical, it's going to try to get rid of that chemical. If you took out some chemical, it's going to try to make more of the chemical that was gone. If you heated it up, it's going to try to cool itself down. That's the idea of the Châtelier principle. Okay, so the reaction is going to shift. And we're going to see the answers of shifting left and shifting right, or making reactants or making products. Those are the types of answers we're going to get for the Châtelier principle. So let's go through the scenarios of all the things you could do to a reaction to disturb it, and then how we can predict what the reaction's response will be. So this is a graphic from our textbook that looks at, well, I would say all of them, but it's missing one. So things that can change are concentration, pressure, temperature, and then our last one is the addition of a catalyst, which we talked about in chapter 14. Okay, so let's start with changing the concentration, which means either pouring in a chemical, it could be pouring in a reactant or pouring in a product, or removing a chemical, removing a reactant or a product. So if the system's at equilibrium already and you add a chemical, the reaction is going to respond by trying to use up that chemical. Okay. If the reaction's at equilibrium and you remove a chemical, the reaction is going to respond by trying to make more of that chemical. So let's look at an equation. There's an equation. Okay, so this reaction was at equilibrium. And then I poured in more hydrogen. So I added hydrogen. The reaction is going to respond by trying to get rid of that extra hydrogen. So the way it's going to get rid of that extra hydrogen is react in a direction that's going to use up the hydrogen. Well, if the reaction goes this direction, doesn't it use up the hydrogen because the nitrogen and the hydrogen both get used up to make the NH3? So if we add hydrogen, the reaction is going to shift to the right, make more products, because that uses up the hydrogen. Well, I didn't have any more examples here, but what would happen if I removed nitrogen? Okay, so if I removed nitrogen, the reaction is going to respond by trying to fix that. Okay, the last time it tried to fix the addition of hydrogen by using up the hydrogen. So that way we don't have any extra hydrogen anymore. If we remove nitrogen, the reaction needs to respond by trying to make more nitrogen because now we don't have enough. So the direction the reaction will make more hydrogen will be if it's going this direction. Because when it goes to the left, hydrogen and nitrogen are products, so it's getting made. So when we remove nitrogen, it's going to be a shift to the left, or you could say more reactants. When we added hydrogen, we shifted right, made more products. All right, let's say we're adding NH3. I want you to stop and think, what do you think is going to happen if we add NH3? How will the reaction shift? Well, if we add NH3, the reaction needs to respond by trying to use up the extra NH3. So which direction does the reaction need to go to use up the NH3? Well, that way. When it reacts to the left, the NH3 goes away. So shift left, which means make more reactants. So those are Le Châtelier principle problems. Now, I change the reaction. I give you a different equation, I give you different chemicals, and I tell you different things about which chemical is being added or removed. Doesn't matter. It follows the same idea. If you add a chemical, the reaction tries to respond by undoing that, which is reacting that chemical. If you remove a chemical, the reaction tries to respond by fixing that, which means making more of that chemical. So let's look at volume of pressure. The textbook calls it a change in pressure. So this only applies to gases. So back in Gen Chem 1, when you learned about gases and all the beautiful gas laws and all that stuff, there was a relationship between pressure and volume. Pressure is pretty much the force being put on something, and volume is how much space it takes up. So when we have a gas, if you increase the pressure, you're smushing it, the volume decreases. So volume and pressure have an inverse relationship. In this situation, it makes sense to me when I think about it in volume, but with pressure, it's just mumbo jumbo. Okay, so when I read the question, a Le Châtelier principle question, and if it uses pressure in the question, then I reword that question in my brain to be volume. So in other words, if the question says, here's a reaction. I increased the pressure. What will it do? Well, increase the pressure. What does that mean with volume? So if I increase the pressure, that means I'm smushing it more. So that decreases the volume. So an increase in pressure is equal to a decrease in volume. A decrease in pressure means I'm not squishing it very much, which means that it is able to expand, which is going to be an increase in volume. So for me, I have to think about it in terms of volume. You may or may not be that way, but in terms of volume, the way the Le Châtelier principle is impacted. Well, when we're talking about volume in a reaction, that means they changed the size of the container that the gases were reacting in. The gases don't have the ability to move to a different container. So when they want to undo what happened to them, they actually can't change the size of their container. So what they have to do is adapt to live into their new container. So let's say a reaction was put into a bigger container, so it had an increased volume. So the reaction's response needs to get bigger to fill its new space. Okay, so it's like if you live in an apartment and then you buy a house and you move all your stuff into the house. Well, your stuff's not going to fill up the whole house. So most people's response is to go buy more stuff to fill up their house. So the reaction, if it's put in a bigger house, it's going to expand to fill that house. So what that means is it's going to shift to whichever side makes more moles of gas. It's going to shift to whichever side is going to make more stuff. Okay. So if the reaction container gets smaller, so the volume decreases, so the container of the reaction gets smaller, the reaction itself has to also get smaller to fit into its smaller house. So if someone's living in a big house and then all of a sudden they have to move into an apartment, they have to get rid of stuff because it's not all going to fit. So this reaction is going to shift to whichever side has the least amount of stuff, which is the fewest moles of gas. So let's look at an example. I know this is the same equation, but let's look at it from this point of view. What will happen to the equilibrium if the volume of the system is increased? So the volume gets bigger. So if the volume gets bigger, that means we need more stuff. We got a bigger house. So we need to decide which side of the equation has more stuff because that's the direction we need to go. So by more stuff, I mean moles of gas. So we're only looking at things that are gases. Well, with this reaction, all of them are. So on the products side over here, there are 2 moles of gas. And on the reactant side, there are 3 plus 1, so there are 4 moles of gas. So if the volume increases, this reaction needs to get bigger to fill its container. So it's going to shift towards the side that will make more gas, which means shift to the left or more reactants. All right, I'm going to ask another question. What happens if the pressure increases? I want us to decide what that's going to do. So for me, when I read that, I'm like, blah, 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 blah. What about pressure? Okay, so I have to like stop and think about it in terms of volume, because that's the only way this makes sense to me. If the pressure increases, that means they're smushing it. They're putting more pressure on it, so its volume decreases. That's not how you spell things. So I'm like, okay, I can't understand that wording, so I'm going to change it to volume decreases. So I need to come back to this reaction and decide, okay, the volume decreases, so the reaction has to get smaller to fit into their new smaller house. Which side of the arrow is smaller? Well, what I'm looking at are the moles of gas. So this side is smaller, the 2 moles, so the reaction is going to shift to the right, which means more products. And you could answer either way. You could tell me shift right or more products. Now, with this, the thing you have to remember, it's different than it is for the concentration one we just talked about. This only applies to gases. So if you have a reaction that has some gases, some solids, some liquids, some aqueous, when you're looking at these numbers, you're only looking at the moles of gases. You ignore moles of solid, moles of liquid, and moles of aqueous. We pretty much always ignore moles of solid and liquid because solids and liquids are dead to us in equilibrium. But aqueous things we also ignore when we're looking at pressure and volume. Okay, so let's move on to temperature. So that would be like, we take my reaction and I put it in an ice bath, or I take my reaction and I put it in a Bunsen burner or on a hot plate. So I change the temperature of my reaction, okay? That is going to matter. It's going to shift the reaction. But in order to answer a question about this, I have to give you a little bit more information. You need to know the reaction that you're looking at. Is it endothermic or exothermic, the way it's written? So delta H greater than 0 means endothermic. So this is a review back from chapter 13. Delta H less than 0 is exothermic. And endothermic means it absorbs heat. And exothermic means it releases heat. Okay. So I have to give you that information. I can either just tell you in words, this reaction is endothermic, or this reaction is exothermic, or I can tell you this reaction, delta H is negative 56, which tells us it's exothermic because it's less than 0, or this reaction, delta H is 142, and it'd be kilojoules, and that would be endothermic because it'd be positive. Okay, so this is how I suggest, once you know if the reaction is endothermic or exothermic, you approach it. If the reaction is endothermic, it's absorbing heat. So add the word heat on the reactant side. So we'll do that here in a second. So heat goes to a reactant. If the reaction is exothermic, that means it's losing heat. It's giving away heat. Heat is leaving. So heat goes on the products side. Okay. If you do that, if you add the word heat to the reaction, now you have to know where to put heat, depending on if it's endothermic or exothermic, then this type of problem works exactly the same way as it does for concentration. So let's do this. So there's me actually showing, like, me adding the word heat on the reactant side or adding the word heat to the product side, depending on if it's endothermic or exothermic. So here's a reaction. There's the same reaction. I was just showing those pretty colors. Goes from blue to pink, and it's kind of purpley in the middle. So there's a reaction. And what I tell you is delta H is greater than 0. So you're going to have to read that and recognize, oh, that means endothermic. And then what we need to remember is endothermic, we're going to add heat on the reactant side. Okay. So what we're going to do now, once I wrote the word heat into the equation. Now, if this reaction had been exothermic, I would have written heat on the other side. So I put heat on the left because of this. Okay. We're going to treat heat like a chemical now. Okay. So we read the question. What will happen to the reaction if heat is added? So if I add heat, the same thing is going to happen as if I had added Cl. So if I add heat, the reaction is going to try to respond by getting rid of it. It's like adding an extra chemical. It needs to get rid of it. So if I added heat, it's going to respond by shifting to the products, which is right, to get rid of that heat. Okay. What happens if I removed heat? In other words, I put it in an ice bath. I made it colder. Okay. So if I removed heat, this reaction is going, oh crap, you took away the heat. I need more heat. It's going to shift to the left towards the reactants to make more heat. You have to write the word heat in the equation. So this, you have to actually do this. Once you do that, treat heat like any other chemical and treat it just like the problems that we've already practiced. Okay. Now, there's only two things I can do with the heat, and I can add it, or I can increase the heat or decrease the heat. Those are the only options. Okay. Now the last thing, the fourth thing, is adding a catalyst. Now the good news, adding a catalyst. In chapter 14, we learned that that means it speeds up the reaction because it lowers the activation energy and usually changes the mechanism. Well, for an equilibrium process, it speeds up the reaction in both directions. So when you add a catalyst, it makes the reaction happen faster forwards and faster backwards at equal rates. So what that means is it's not going to shift in either direction because it impacts it equally. So when you add a catalyst, there will be no shift because the reaction happens faster forward and backwards. Ba-bam. Okay, so let's practice. Okay, what I want us to do is look at these three reactions, and I want us to think about how they're going to shift if we decrease the volume. Okay, so when we're dealing with volume, that means we're looking at gases only. Gas, 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 gas. They're all gases, okay. So when the volume is decreased, that means the reaction needs to get smaller. That means less moles of gas, fewer moles of gas. I always forget which one is the correct term for that. So let's look at the moles of gas. Well, there's 1 and 3, so there's a total of 4. And then there's 2. So which direction will this shift if it needs to get smaller and go to the fewer moles of gas? Well, towards the 2, which is the smaller number. So it's going to shift to the right. Okay. I'm going to skip down to the third one first. This one has 2 moles of gas. This one it has 2 plus 1, so 3 moles of gas. So if it's going to shift to get smaller, it needs to shift towards the 2, which is smaller than the 3, which means left. Okay, let's look at the middle one. There's 1 mole of gas and 1 mole of gas, so 2. There's 2 moles of gas, so 2. It needs to shift to get smaller. Well, which number is smaller, 2 or 2? That means there's not going to be a shift because there's not a better direction for it to go. Okay, let's try another example. This one, I'm mixing it all together. There's my reaction. And just to emphasize this, I'm going to write a positive sign right there. I want us to decide what will happen if I add nitrogen. So we need to think about how will this shift. So I want you to take a second. Actually, why don't we just take a second, and I want you to try to answer these, and then we'll come back and talk about them together. So hit pause, answer these 4 things, and then we'll go through it together in a second. Okay, so I add nitrogen. We have too much nitrogen. We have to use up the nitrogen. So it's going to shift to use up the nitrogen, which will be shift to the right or towards products. The second one says the reaction mixture was heated. Oh crap, heat. We got to add the word heat. So we got to go look at the delta H number. It's positive 92.4. So that means it's endothermic. If we look back at that chart, endothermic things, we're putting heat on the reactant side. So if we're adding heat, we have too much heat, we have to get rid of it, so we need to shift to get rid of it. Well, that's going to be shifting to the right. Okay. If NH3 was removed, so if NH3 was removed, then this reaction needs to shift to make more of it, which would actually also be shifting towards the right. And then our last one is if the pressure of the container was decreased. All right, so I got to switch to volume. So if the pressure was decreased, It's not pressing on the system as much. So the system is able to expand. So it's going to be an increase in volume. So if it's an increase in volume, we need more stuff to fill up our bigger container. So we have to look at our reaction to see which side has more stuff. 1 mole on 3 moles is 4. 2 moles is 2. Again, we're only looking at gases. So it's going to shift to the left towards more moles. Okay. The Châtelier principle problems are not math. They are, is it going to not shift at all? Or is it going to shift to the left or shift to the right? Those are the types of answers you're going to be giving for these Le Châtelier principle problems.